Have you ever, actually stopped to wonder why your car engine doesn't just rattle itself into 1,000 pieces while you're flying down the highway at 70 miles an hour?
Right. Or even something way simpler, like grabbing a glass bottle of soda from the fridge.
Yes,
Yeah.
exactly. That bottle's it completely pressurized. Why doesn't it spontaneously explode in your hand the second you pick it up?
Because, I mean, we just simply expect the physical world to hold together, right?
We do. We totally take it for granted.
We demand this crazy level of physical perfection in our daily lives, from the airplanes we fly in to the medical devices we rely on. And it's mathematically astounding when you look under the hood.
Yeah, we are constantly walking across this web of invisible safety nets. And really, that brings us to the mission of our deep dive today. We are going to explore the hidden mathematical architecture of the physical world.
The secret, incredibly rigorous code that keeps everything functioning.
Exactly. And our guide for this exploration is, it's going to seem surprisingly mundane at first glance.
It really is. We are pulling our insights from a textbook chapter today, specifically Chapter 8, Introduction to Statistical Quality Control.
Now, I know what you might be thinking. Statistical quality control sounds like the ultimate cure for insomnia.
It sounds incredibly dry.
But I promise you, it is the secret language of reality. It is the literal difference between a safe drive to work and a catastrophic mechanical failure.
We're going to see how factories attempt to measure a single perfect part,
Right.
and the terrifying mathematical blind spots that trick engineers into thinking a failing product is safe.
Yeah. And finally, what happens when human beings themselves are used as measuring instruments? Okay, let's unpack this.
Yeah. So to really grasp how the manufactured world operates, we have to define the concept of good enough.
Right. Because perfection is basically impossible.
Exactly. Engineers don't just guess.
Mhm.
They use something called process capability analysis.
Mm.
At its core, this is a strict comparison.
Okay, comparing what exactly?
It compares the inherent natural variability of a manufacturing process against the rigid specifications required for the product to actually work.
Right, because nothing in the physical universe is perfectly identical. If a factory churns out 1 million glass bottles, every single one of them is going to be microscopically different.
Yeah, and the source uses that exact example, the bursting strength of glass containers.
Which is pretty important. If you're holding a pressurized beverage, bursting strength is literally a life or death safety parameter.
It really is. And the math gives us a ratio for this, called the process capability ratio, or CP. The textbook states that for a critical safety item, like a glass bottle, the acceptable CP needs to be at least 1.45.
Okay, so that ratio tells a specific story. It's the width of your specification limits, like what the design safely allows, divided by the natural statistical spread of the process itself.
Right, but there's a catch. C only tells you the potential capability of the process.
Wait, potential.
Yeah, it assumes your manufacturing line is perfectly centered on its target. That assumption is why engineers had to create a second ratio called CPR,
Ah, okay.
which measures the actual capability by calculating where the process is truly operating relative to those safety limits.
Okay, I think I have an analogy for this. So CP is basically the size of your garage, and CP is how well you are driving down the center of it.
Oh, I like that, yes.
Right. Like, if you have a massive 2-car garage and a tiny compact car, your CP is huge. You have immense potential to park without an incident.
But CP is about the reality of your driving.
Exactly. You might have that massive garage, but if you're drifting way over to the right side, you're still going to scrape your passenger side mirror against the wall.
Which means your CP is terrible because you aren't centered.
Exactly.
And, the engineering world didn't stop there. They realized that even CPI had limitations in how it warned operators about that drift. So they developed a third-generation ratio called CPM.
Okay, so what does CPM do differently?
What's fascinating here is how CPM actively penalizes the mathematical score the further your average gets from the actual target.
Oh, interesting. How does it do that?
It does this by squaring the difference between your process mean and the target value.
Ah, so by squaring that number, the penalty grows exponentially.
Right. If you start drifting away from the ideal center of your garage, CPM acts as a highly sensitive alarm system. It's like screaming at you long before you actually hit the wall.
And the numbers attached to these ratios are staggering when you look at the real-world scale.
Absolutely.
Like, the source notes that a CP of 1.0, which means your process spread exactly matches the width of your specifications, that results in about 2,700 defective parts per million.
Which might sound like a tiny fraction.
Yeah, it sounds great. Until you realize that if an automotive supplier is making 50 million brake components a year, 2,700 failures per million is a massive liability.
It's totally unacceptable. That is precisely why modern manufacturing pushes for Six Sigma levels of quality.
Right, aiming for a CP of 2.0.
Exactly. And just to clarify that term, a sigma is simply a standard deviation, a mathematical step away from the center of the bell curve.
Okay.
So if your process has a CP of 2.0, it means your specification limits are a full 6 standard deviations away from your process average.
So your garage is so incredibly wide compared to your car that your failure rate just plummets.
It drops down to 0.00018 defective parts per million. You are virtually eliminating the possibility of a defect.
Wow. That is an incredible illusion of perfection, but I feel like it leads us directly into a massive vulnerability.
It really does.
Because we've established how companies measure success, but what if the map we are using doesn't match the territory?
Yeah, what happens when the mathematical assumptions underlying these precise capability ratios are completely fundamentally flawed?
Right. It raises an important question. What happens when reality refuses to follow the rules of our equations?
Because almost all of these capability ratios, like CP and Cpk, they rely on one foundational assumption.
That the data follows a normal distribution.
Yes, the classic symmetrical bell curve.
Where most things cluster perfectly around the average, fading out equally on the high and low ends.
Exactly. The problem is that the real world is intensely messy.
So messy.
The source provides a brilliant example regarding the surface roughness of a machined metal part. When engineers measured the parts and blindly fed the data into their software, assuming a normal bell curve, the math declared that the failure rate was less than 1 defective part per billion.
Wow. 1 in a billion. It looked like they had achieved absolute engineering perfection.
They really thought they had.
Wait, if the data didn't look like a symmetrical bell curve, what did it actually look like?
It was highly skewed. Instead of a gentle symmetrical bell, the data looked more like a steep cliff.
Okay, why?
Because the physical nature of the machining process meant there was a hard limit on how smooth the part could get. But occasionally the machine would leave a deep anomalous gouge. So the data clustered heavily to one side with a long trailing tail on the other.
Wait, if the math is that sensitive to the shape of the data, why do people just blindly trust the software output?
Well, think about it. If a computer spits out a failure rate of 1 in a billion, human nature is to celebrate, not to dig into the algorithmic assumptions buried in the code.
That is so true. But that false sense of security is the ultimate danger here, isn't it?
Absolutely.
Right.
You have highly sophisticated software generating very precise but utterly meaningless numbers.
So how do they fix it?
To fix it, the statisticians in the source text had to transform the data. They used the reciprocal of the surface roughness measurements.
Okay, let's break down what taking a reciprocal actually does in this context, because that sounds like mathematical sleight of hand.
It kind of is. Think of it like looking at a funhouse mirror. The raw data for those metal parts was stretched out, creating that long, skewed tail of rough parts.
Right.
By taking the reciprocal, essentially dividing one by the measurement, it mathematically flips the perspective.
Okay, so it squishes that long tail back in.
Exactly. Forcing the data into a neat, symmetrical bell curve that the standard formulas can finally read accurately.
And once they did that, what happened?
The true failure rate was revealed to be 3,350 parts per million.
Oh, wow. It went from 1 phantom defect in a billion to well over 1,000 actual physical defects in a million.
Yes, you could be shipping out thousands of failing, potentially dangerous components, completely confident that your process is flawless.
Just because the computer spit out a reassuring decimal point.
Exactly. And the illusions don't stop at the shape of the curve. You also have to assume process stability.
Right, because you fundamentally cannot calculate a valid capability ratio on a manufacturing process that is unstable.
No, you really can't. If a machine's temperature is wildly fluctuating from hour to hour, calculating an average of those chaotic fluctuations to find your CP, it gives you a number with zero predictive value.
It tells you literally nothing about what the machine will produce tomorrow.
Right. But the reality of corporate bureaucracy is that management demands those numbers anyway.
Yeah, the textbook points out this wild mandate from the automotive industry. It required parts suppliers to calculate performance indices, specifically metrics called PPU and PPK, even when a process was actively known to be out of control.
And the authors of our source, Coates and Lovelace, actually lose their academic composure over this.
They do. They call this mandated practice undiluted statistical terrorism.
It is a phenomenal phrase, and honestly, it is entirely justified. Forcing an engineer to calculate a metric for an unstable, wildly fluctuating process is worse than useless.
You are basically weaponizing the language of statistics to intimidate a supplier into providing a number just to satisfy a corporate checklist.
And everyone involved knows that number is a complete fabrication. It provides zero insight into the quality of the product.
Instead of spending time fixing the broken machine, engineers are forced to perform bad math to appease a spreadsheet.
It's maddening.
So bad algorithms and bureaucratic mandates can completely blind us. But let's say you fix the algorithm. Your equations are flawless and your process is perfectly stable.
You still have a massive physical vulnerability.
The actual ruler you were using to measure the part in the first place.
Right. If your measuring tool is flawed, it doesn't matter how beautiful your equations are.
So we have to check the checker.
We do. This discipline is known as Gauge and Measurement System Capability, or MSA. Whenever you look at variation in a product, you have to partition that variance.
Meaning you have to figure out how much of the wobble in your data is coming from the actual physical product and how much is just noise coming from a sloppy measuring tool.
Exactly. And the source breaks this measurement problem down into two key concepts: repeatability and reproducibility.
Okay, so repeatability is the basic test of the instrument itself. Like if I use this exact same digital caliper to measure this exact same metal bolt 5 times in a row, does the caliper give me the exact same number every time?
Right. And reproducibility tests the environment and the humans involved.
Ah.
If I hand that caliper to you and then to a different technician on a different shift, do we all get the same number? Does the measurement hold up across different operators?
The text highlights a specific study on this, right? With a thermal impedance power module.
Yeah. They took 10 individual parts, had 3 different human operators, and had them run 3 separate tests each.
And by structuring the test that way, the engineers could mathematically isolate the chaos.
They could determine that, say, 10% of the variation was the testing machine drifting, 5% was the difference in how the operators handled the module.
And the remaining variation was the actual difference between the parts?
Exactly. Partitioning that variance is vital because a sloppy measurement system creates 2 devastating real-world scenarios. The first is called producer's risk.
Which results in false failures.
Right. This happens when the measuring tool is acting up and tells you a perfectly good, flawlessly manufactured part is actually defective.
So the factory ends up throwing away a perfectly good product, which just destroys their profit margins.
Yeah, but the second scenario is the one that directly impacts everyone listening to this.
Consumer's risk. Missed faults.
Yeah. This is when the sloppy gauge looks at a genuinely defective, dangerous part and registers it as completely fine.
So the factory ships a faulty brake pad or a weak glass bottle out into the world.
Exactly.
Here's where it gets really interesting, though. We've been talking about physical instruments, calipers, thermometers, pressure gauges, but the source pivots to something much more unpredictable.
Oh, human beings.
Yes. What happens when the gauge taking the measurement is a human being making a judgment call?
This takes us into the realm of attribute gauge studies. An attribute isn't a continuous number like voltage or weight. It is a binary human decision. Pass or fail. Accept or decline.
And the source details this extensive study involving mortgage loan underwriters acting as the measurement system for financial risk.
The details of this study are crazy. They'd completely shift how you view the financial system.
Seriously, the researchers took 30 actual mortgage applications and stripped out all the identifying information.
And they gave these 30 blind applications to 3 different professional underwriters. Each underwriter had to evaluate all 30 applications twice, separated by several days.
Right. And finally, all of those individual decisions were compared against a baseline consensus evaluation made by a senior panel of banking experts.
So the structure is identical to testing a factory caliper. We're testing the underwriter's repeatability. Like, do they make the same decision on Tuesday that they made on Thursday?
And their reproducibility. Do the 3 underwriters agree with each other on the exact same financial data?
Exactly. And these are highly trained professionals evaluating people's life savings and housing futures. You would assume the agreement would be incredibly tight.
But the data revealed that the percentage of agreement between all the appraisers was a staggering 23.33%.
Yeah, less than 1/4 of the time did these professionals look at the exact same numbers and reach the exact same conclusion.
That is wild. It exposes just how noisy and subjective human judgment truly is.
When the human is the gauge, the measurement system is inherently unstable.
It really suggests that getting approved for a life-changing loan might depend less on your actual financial capability and more on whether a specific underwriter happens to pull your file before or after their lunch break.
It's a terrifying thought. And this subjective chaos is exactly why engineers fight so furiously for hard physical measurements in the manufacturing world.
Yeah, but measuring one single component perfectly is still only half the battle, because your car isn't a single solid chunk of metal.
No, it is thousands of individual parts that have to interact.
Right. So how does quality control work when you start combining things together?
We enter the concept of tolerance stack-up. This is where the mathematics of quality control become incredibly unforgiving.
Because when you assemble a complex system, the microscopic variations in the individual components don't just sit in isolation.
No, they accumulate, they stack up.
The text starts with a simple linear example. Imagine a mechanical linkage made of 4 separate components bolted end to end.
Right, and if each of those 4 parts varies just a tiny fraction of a millimeter in length, engineers have to use statistical formulas to predict if the final total assembly will actually fit into the machine it's designed for.
But the linear examples are straightforward addition, right?
Yeah, the true complexity arises when the relationships between components are nonlinear. The source uses the delta method, also known as the transmission of error formula, to demonstrate what happens in a basic electrical circuit.
Using Ohm's law, voltage equals current times resistance. V equals I times R.
Exactly. Because the components are being multiplied together to create the output, their underlying statistical errors multiply as well.
And the source provides the specific parameters for this circuit. The engineering design requires a final output of 100 volts, with an allowable safety margin of plus or minus 2 volts.
So to build this, they select a component that provides a current of 25 amps plus or minus 1 amp. And they use a resistor of 4 ohms plus or minus 0.06 ohms.
And if you look at the current and the resistance individually, their variation seems totally fine. They are well within their own passing specifications.
And because of how they interact.
It's exactly like a group project in school. Everyone individually does B- work, technically passing. But when you staple all those mediocre sections together, the final presentation doesn't make any sense, and the whole project gets a failing grade.
I love that analogy, yes.
Yeah.
The mathematics of tolerance stack up guarantee that failure. Individually, the components passed inspection. But when you multiply them together, the variation explodes.
Wow.
The source calculates that because of this compounding error, only 84% of the assembled circuits will actually hit that required output of 100 volt.
Meaning 16% of the surface built with perfectly acceptable parts will fail right off the assembly line.
Right. The overall process capability, the CP for the entire system, collapses to 0.47.
And remember, we established earlier that we need a CP of 1.45 for basic safety and 2.0 for Six Sigma excellence.
A CP of 0.47 means the system is fundamentally broken. If we connect this to the bigger picture, this multiplying effect of errors is why the philosophy known as design for Six Sigma was created.
You cannot just manufacture good individual parts, throw them in a pile, and expect a reliable system.
Exactly. Engineers must design the entire architecture from the top down to absorb, mitigate, and account for the inevitable compounding wobble of its pieces.
So, what does this all mean for you listening right now? It means that the physical world you interact with every single day is a breathtaking miracle of statistical balancing acts.
It really is.
The next time you turn the key in your ignition, or submit an application for a mortgage, or simply open a pressurized glass bottle of soda, take a moment to appreciate the invisible mathematical safety net. The complex equations, the standard deviations, and the rigorous capability ratios that are constantly working behind the scenes to guarantee that the world operates smoothly and safely.
And I will leave you with one final deeply provocative concept pulled from the very end of our source text.
Oh.
What's that? The chapter concludes by discussing natural tolerance limits. It acknowledges a very uncomfortable reality. Despite all our formulas, we often do not know the true underlying distribution of a physical process.
Oh, wait, really?
Yeah, we don't actually know if the universe is providing a perfect bell curve. In those situations, engineers are forced to use non-parametric limits.
Which means doing what exactly?
It means they abandon the theoretical curves entirely. They simply run the process, look at the extreme largest and smallest measurements they happen to catch in that specific sample, draw a box around them, and assume that those extremes represent the boundaries of reality.
Wait, so they are essentially designing the safety limits based purely on the absolute worst things they happen to observe on that particular Tuesday.
Precisely. Which leaves you to ponder this. In a universe defined by infinite variables and endless compounding chaos, do we ever truly know the exact mathematical shape of reality? Or is the entirety of our modern, precision-engineered world, the skyscrapers we work in, the airplanes we fly in, the medical devices in our hospitals, ultimately balanced on nothing more than highly educated, statistically acceptable best guesses?
A highly educated guess that keeps the glass bottle from exploding in your hand. I think I'll drink to that.